this opportunity to be here. Before I start with my presentation, I would like to say, okay, yeah. Before I start with my presentation, I would like to read a short paragraph about Professor Minzoni. And I go. Professor Minzoni accompanied my research since the first semester of my PhD that I started here at IMA, supervised by Professor Panayotaros. He becomes like my second advisor. During this time, I learned a lot with him about mathematics, physics, history, ancient battles and wars, and politics. He was very proud of his high-level education, and he used his skills to improve and to impact enormously the academic life of this university. He was always the promoter and the generator of very useful and enlightening discussions. He was a fantastic storyteller, and he shared with us his good memories. I enjoyed every course and seminar I attended with him. It was impressive his ability to see through the equations and the theory. He could imagine tons of very useful toy models, cartoons of physical phenomena, and simplify approximation to complex equations, very useful in physics, biology, and medicine. With his experience and knowledge of a great number of theories in physics and mathematics, he developed a remarkable intuition and a very particular and special way of thinking. He was always looking for challenging problems to work on it, and I will miss him a lot. Okay. Bueno, Professor Minzoni and Professor Panayotaros conveyed to me the interest in surface water waves, and this is the topic of this talk. I will talk about the fascinating theory of surface water waves and a Guidan-Boussinesq model. This is a joint work with Panayotaros and Minzoni. This is the outline of the presentation. I will start with a gallery of surface water waves. I will show a bunch of movies and figure and picture of these amazing surface water waves for the people in the audience that are not familiar with. And then I will state the theoretical framework of the problem, the water wave problem, that involves the Hamiltonian formulation of the water wave problem, the Dirichlet-Neumann operator, and pseudo-differential operators. With this theoretical framework, we can state our Guidan-Boussinesq model, and then with the aim to test the accuracy and performance of this model in surface wave, I will show you some recent results on normal mode in non-trivial geometries. Okay. In this slide, you can see the surface water waves in very different contexts. In the middle, you can see a tsunami wave generated in the earthquake of Sumatra in 2014 that propagates in the ocean. And I don't know. And also you can see these standing waves generated in a water wave channel in a lab, and a solitary wave traveling also in a water wave channel, and the elastic collision of two solitons propagating, driven by the KdV equation. Also, in this slide you see water, the normal mode that you can compute on a straight channel with different cross sections, with different geometries, and this is important in industry, in particular for the design of the shape of different fuel tanks. Okay, the physical problem that we want to study and to describe is the propagation of surface water waves over variable depth. And as you can, these videos has been generated with the data we collected from our numerical simulation using our Williams model, and we see an standing in the left. We see an standing wave that, the second order stock waves of the Euler equation that should behave like an standing wave. But when you, as you can see in the picture, but when you introduce the topography, you see that this behavior, this standing behavior, is destroyed by the topography. Also, this is other example of a modulate wave that in constant in depth, you see that the wave splits into waves that travels in two opposite directions at constant, and the wave crest travel in constant velocity. But when you introduce again the topography, the wave profile is destroyed, and also the wave crest propagates at different velocities. Well, as you could appreciate all these videos and pictures, because the waves, the surface water waves, the gravity surface water waves, evolves on a time scale that humans can naturally relate to, as opposed with electromagnetic, where you need to use a very sophisticated experiment like Gaetano and Karen Polke showed to us. And well, there is this is like the particles behave when a wave is traveling, and well, the particles travel in a clockwise direction, and the radius of the circles decreases as the depth in the water increases. So shallow water feels more the bottom topography, and when I talk about shallow water, is a physical regime where the wavelength of the surface wave is long relative to the mean depth of the fluid. So also other characteristic of the surface water waves is that they propagate with little dissipation, and also that the waves are dispersive. And this means that the waves of different wavelengths travel at different speeds. And in this picture, you see a capillary waves, where are created mostly by the effect of surface tension. And you see that the long wave travel slower than the shorter waves. But in this picture, you see the opposite behavior with the long wavelength. Here, in this case, when you consider the effect of gravity and the long waves travels faster than the shorter waves. So this is a dispersive behavior of the waves. So the fluid we are interested in modeling is inviscid, homogeneous, incompressible, and irrotational. And the only volumetric force acting on the fluid is gravity. And with this assumption, we can describe most of the waves that I showed you before. Well, the fluid domain will be simple connected, could be in 2D or 3D dimensions. And these are the quantities of the problem, the important quantities. L is the wavelength, H0 is the mean depth of the fluid domain, and beta x is the variation of the topography from this H0. It's an also, when we have the characteristic that is an irrotational fluid, and this allows to give a description of the velocities of the fluid in Eulerian coordinates as the gradient of a hydrodynamic potential. And with the equations, the well-known Euler equations, describes the propagation of surface water waves in a fluid domain with this characteristic that I mentioned before. And these are the Euler equations. The hydrodynamic potential is harmonic and should satisfy these three boundary conditions. The bottom is impermeable, so it's a normal derivative equals 0 there. And these are the conditions in the free surface that are a couple equations, of non-linear couple equation. And in general, there is not a general solution for this equation, and you should look for special physical regimes or for special assumption to derive simplified models. Well, as you see, the evolution of eta and the amplitude of the profile and the potential are in terms of the normal derivative and the tangential derivative on the surface quantities, on the eta profile and on the surface potential. But in order to evaluate the normal derivative of the surface potential, you need to solve this elliptic problem at each time of the time evolution of the wave, and because when the profile change, the potential change, and when the potential change, again the potential is transformed. So at each time, you should solve this elliptic problem, and when you obtain phi, you compute the normal derivative of phi, and then you evaluate this normal derivative in the surface. And this is the definition of the Dirichlet-Neumann operator. You give an initial potential in the surface, and then you compute the normal derivative of this potential, and this is the definition of Dirichlet-Neumann operator, because you get the Neumann, the Neumann condition of the potential, no? And well, these remarks allow Sakharov to see that this water wave problem can be stated as a Hamiltonian system, as an infinite Hamiltonian system in terms of these surface quantities, the profile and the potential in the profile. And these are the canonical Hamiltonian equation to obtain the evolution equation that we have here, in the Euler equations. And then later, around 30 years later, Craig and Sulem introduced explicitly the Dirichlet-Neumann operator in the Hamiltonian of this system, and they arrived to this very elegant expression of the Hamiltonian of the water waves problem. And well, when you use the Hamiltonian formulation of the water wave problem, you need to know that in general there is not a explicit expression of the Dirichlet-Neumann operator. And the only explicit expression that exists is when you consider this fluid domain with flat bottom and with zero amplitude of the wave profile. So it's not the interesting case. But in this case, you know that the normal derivative, when I put in the operator the initial potential in the surface, I get by evaluating this operator in the potential, I get the normal derivative of the potential. And this operator is performed of this way. D is this differential over X, this differential operator. And well, I should take the initial potential, then transform to Fourier in the Fourier space, apply at the Fourier transform to the potential, then multiply for this amount, and then again apply the inverse Fourier transform. So these operators are well defined in the Fourier space. Well, this is a Fourier multiplier. Then we will work with a generalization of this kind of operators with pseudo-differential operators that appears also in the formulation. Well, many people have worked on this problem since this formulation has been established in order to get more stronger or more general results to general topographies. And well, the first, all these authors, I can mention all these authors, and considering a small variation in the amplitude and variation of the topography of order 1, they give an expansion of this operator. It's a Taylor expansion when beta is, well, no, they give an expansion of this operator. And those are the first term of the expansion. And we can see that the effect of bottom topography here is in the first term of the expansion of this pseudo-differential operator, considering this assumption. And this term is the only term that captures the effect of the topography. Well, from here, when you consider variation of the topography of bigger order, there is not an explicit expression of this operator. And Craig, Guyen, Nichols, and Sulem give us a semi-explicit form of L beta operator, and this form is in terms of these pseudo-differential operators. Well, an alternative expression of L beta operator is in powers of the depth variation, as a infinite series of pseudo-differential operators that are in this that have this form. So those are exact analytic results, and most of these authors also have tried to compute numerically these operators and to obtain simplified models of the water wave equations. And well, with this using this expansion of the operator and assuming a long wave asymptotic regime, where, as I said in the beginning, these two non-dimensional parameters are small, well, only delta and epsilon are small. Delta is the radio between the mean depth and the wavelength. And assuming this is small, and also is the amplitude, as I said, is small, and epsilon is small, we can neglect many of the terms of the expansion of this pseudo-differential operator, and at least in this regime, we can obtain simplified model. And in the case of flat bottom, the formulation is very accurate using these non-dimensional parameters. But when you introduce the variation of the topography, the community doesn't have a very accepted and very used simplified model. So this was the aim of the research, to derive a simplified model that can capture the variation of the topography and great variation of the topography. And well, in the next slide, I will show you different approach to this differential operator. The easiest one is assuming flat bottom, and we obtain this operator that we substitute here, and then we compute the canonical equation of the Hamiltonian, and we obtain the system, no? And also, Aceves, Minzoni, and Panayotaros in 2013, they proposed another simplified operator, but now with the topography. And they assume a small variation of the topography, and then in order to, with the aim to get an explicit expression of this operator, not an L beta, but an explicit expression. And they arrived to this model. All of these models are dispersive, and that means that they keep the exact dispersive relation that you can measure from the Euler equation, the linearized Euler equation. And this is very important in order to have a model that is loyal with the reality and to capture many of the effects of the solutions that you can see in reality. And there are also, again, many people working on this Whedon type model, and they have proved the existence for this kind of model of periodic traveling waves, solitary waves, wave breaking, and Q-speed waves. So it's very general. And when finally I show you our model that is given in using this pseudo-differential operator that gives the same structure of the Dirichlet-Neumann operator, that is symmetric, is real valued, and recover the constant depth operator at high wavelengths. And it seems that it looked like a simple expression. Okay. And when we tested our operator with this modulate wave packet, because this was the experiment that Craig and Sulem report in his article, And the thing that I wanted to see that we recovered the same, the same, well, the same behavior on almost the same, picture, but they use 5 terms on the expansion of the pseudo-differential operator. And when they want to introduce to topography, they need to use even more terms on the expansion to obtain, for example, this very complex experiment that consists in the propagation of a soliton over a sloping beach. And for obtain a good model to reproduce this behavior, they use up to 8 terms on the expansion and, well, 2 terms on L beta operator expansion. Well, we didn't follow this way. This is a future work to test the operator with the soliton, but we did the other thing that I will show you in a few minutes. But also we test the, well, we integrate numerically the evolution equation with an Adam Bashford Fulton, I don't know. Adam Marshall, of fourth order or 5 order, I don't remember. And we these are this picture show the sensitive of our numerical scheme to the time step, and also with the resolution that we use to discretize that. I didn't tell you, but the main work that we did when we introduced this model is it was the discretization of the pseudo-differential operator. It was like the first problem that we needed to solve in order to have this, not only the abstract model, but effective model that we could simulate waves with this model. So we did a discretization of this operator, and this is a very long and technical way, and too much work, and I will not show you. But also, in previous work, we did an spectral study and analysis of this operator, because we arrived to a discretization of a matrix representation of this operator. We arrived to a matrix representation of this operator in Fourier space, and for the result that I showed you in the beginning, these 2 videos, we only needed 2 to the 6 modes for an accurate simulation, using an spectral method. No? Oh well, the next motivation was to examine the accuracy of this approximation with topography. No. For that, when I remember that Minzoni recommended us to study trapped waves, and we did it. We studied and we sent it to the review, to the magazine or to the review, and well, we sent the result that I will show you in a moment, and also this trapped wave result, but they wasn't convinced about the good performance of our operator with the topography, and they needed more proofs of the accuracy and of the behavior of this operator compared with other standard operator or simplified model that had been studied in the literature. And that's why we decided to look for exact solution, look for a problem that has some exact solution, and that's why we arrive to the normal modes in non-trivial geometries. And in non-trivial geometries, and well, the idea is that you look for transverse modes and longitudinal modes on this channel with this cross-section geometry that have this shape. You plug in the linearized Euler equation these solutions, and you arrive to a transcendental equation that you solve. Well, you solve by the crossing of the graphs of this transcendental equation, and you get the exact combination of kappa and omega that gives you the normal modes of this geometry. And well, with the problem, to solve this problem, you can solve this, obtain this normal mode, but in flat bottom, for example, with these two operators that have the same shape of the operator that the water void problem has, and then you introduce again the topography by this operator, and there are only no solution for these 4 geometries, and I will show you the result that we get comparing the solution with this geometry and this geometry with our operator, and with this other operator that was being derived by Craig, Guyen, Nikos, and Sulem, and also with this operator that is the Taylor expansion in the variation of the topography of this operator. Also, we compare the solution we get from all these operators for this case of this triangular, and well, this is with our operator is in cyan color, and in red is the operator of Craig, Guyen, Nikos, Sulem, the simplified operator. This is for even modes, and this is for odd modes. And well, you can see that we have a good fitting. All the models have good fitting with even modes, but there is not a very good fitting with odd modes in the corners on the boundary of the channel. And using the second, the first order, the Taylor approximation of the first order in the variation of the topography, we obtain this result that, well, looks a little bit worse in this case. But the important is that our operator now has been tested with an well-known operator derived by Craig, Guyen, and Sulem, and has a good performance. And well, we continue to do many tests and other things that I will not show you today. But yeah, it's all. Sorry. No, de veras que no doy una.
Questions?
What happens to your equations if the free surface hits the bottom?
If the free surface hits the bottom with the operator, or
Do the equations stop, or do they continue to give solutions?
You should assume that it's a simple connected domain and there is not any island, so the bottom never touch the surface. So this is a problem with this evaluation of this mode, because there is 2 points in the triangular channel where the Dirichlet-Neumann operator are not well defined because they assume a condition on the surface and a condition on the bottom, and that's why yes, there is. This is we need to explore how to improve this formulation in order to be able to capture these geometries, these sloping geometries.
So it stops.
Stop. Yes. Okay.
John?
Yes. Yes, we reproduce everything. The width and models in flat bottom is totally reproduced. Yes. They are what?
Tavo?
I don't know if this just modify a little, but Craig, he did he yes, he used a parameterization.
Any other questions?
Yes, it's a little modification.
Yes, John. Yeah, you.
Sakharov. Sakharov. Hamiltonian. Is that I didn't follow the question, sorry. This is Hamiltonian, yes. The energy of the system. Yes, this is and the proof consists to arrive from the kinetic, the usual expression of the kinetic and the potential energy, and to see that with the introduction of the potential, you reduce this Hamiltonian classic formulation using this pseudo-differential operator. Okay, no.
More questions? Okay, let's thank our speaker again.
Bueno, es que tú hablas muy bien, por eso te pregunto. Ah, esto.
Next speaker is Alfredo San Juan from Instituto de Materiales UNAM, and the name of the talk is The Form of a Drop Immersed in a 3D Elongational Flow.
Ok, también la tiene. Ok, también la tiene. La de... Good afternoon. Today I will talk about drop deformation. This issue it's a topic in fluid mechanics. Was the last that I worked with team. This is our this is our group of research at Materiales. This is my advisor, Professor Freud, Professor Minzoni, and Professor Marco Reyes. Today, I will deform a drop in an extensional flow. What does it mean? Imagine a drop immersed in another fluid. We start with a drop at rest, then we turn on the flow, and we apply this flow in the fluid which contains the drop, and we will observe how the drop is deformed. This is the three-dimensional diagram. We will have an elongation axis, that is y-axis, and we push the drop in the other directions. So this is a perspective of this body in 3 dimensions. This is the velocity field that we use. In this case, G is the strength of the flow. It is the strain rate. We push in the x-axis and the y-axis, and we elongate in the other. Okay. The movie of the phenomenon and we deform the drop, and then we wait until we attain the steady state of deformation. To study drop deformation, we need to study 3 parameters. The capillary number, that is the competition between viscous stresses and interfacial tension stresses. The ratio of viscosity, that is the viscosity of the drop over the viscosity of the media, and the deformation of the drop. As you saw, this is the principal axis of elongation that I will call L, and perpendicular to this axis I will call B. This is the major axis of this drop, and this is the minor axis of the same drop. So the deformation is L minus B over L plus B. In this case, we have a drop with a value of capillar 0.20. The deformation at time is 0.25. The rate of viscosity is 1 over 100. This is the numerical formulation. I use boundary element method in 3 dimensions. This is the equation that I solve every time, and has 4 parts. The first is the flow that I impose over the fluid. The second and the third are the integral formulation to solve the Stock equation using the second theorem of Lorentz. What does it mean? To solve the velocity on the surface of the drop, I will use an analytical solution which solves Stock's equation, that is the Stocklets and the stresslets, which are the velocity and the stress field of a point sources over on the surface. I have the jump of the stresses over the surface, and I have to compute the velocity on the surface. The idea to observe the steady state of deformation of a drop in this kind of fluids is not a new idea. In 1988, Acribos and Law developed a theoretical method to obtain the shapes of the drops in that kind of flow. This is the original diagram, and they consider first the case axisymmetric, so they only solve one part of this drop. They estimate the radius of the drop in this direction as a function of the large axis of elongation. The other consideration they made was that outside and inside the flow, the streamlines of the flow are hyperbolas. This idea means that the drop does not have viscosity. It is the ratio of viscosity is 0. The ratio of viscosity implies a facility to deform the drop. It is, if the drop is very viscous respect to the other fluid, the deformation we can apply to the drop will be small. In the other case, the deformation will be huge. This is the case Akribos and Lowe take. They solve Stokes equation using slender body theory, and they obtain this this function as this. We see the capillary number, this parameter nu, which depends of the pressure, but nobody knows what is the value of nu. We have a positive value of nu from 0 to 1, we recover the hyperbolic profile. In the other case, if nu is bigger than 1, for example 2, we have a shape similar to a drop deformed in this kind of fluids. Then, with this information, they develop a diagram of stability which relates the principal elongation axis of the drop and the capillary number. There is the ratio of viscosity, and we have two branches. This branch is stable, and this can be obtained with elongational flows. In the work in 1978, they found that this was unstable. So today I will show what's happened if the drop has a value of the ratio of viscosity different of 0, because this schema was made consider no viscosity on the drop. In this part of the diagram, we will have slender drops. In this case, we will have drops with a small deformation. This case is this analytical solution of Akribos and Lowe for this diagram. I made the same experiment using the numerical model, and I have this smooth shape. The model of Akribos and Lowe is very similar to a football balloon, and to obtain the branches of solution is with this equation. Again, in this part, we have the critical value of the capillary. What does it mean? Capillary number, when you have a capillary number that is critical, the drop will deform and deform and deform, and you can never reach a steady state of deformation. So, with that information, we estimate the capillary number approximately to remake another experiment. In this case, we have the principal axis of the drop, B and L, and we observe that the drop doesn't change. So we attain the steady stationary. So we have the value near to 2, and we estimate in the diagram where it is this point. In the other case, we introduce a huge drop, and then when we apply this capillary number with this ratio of viscosity and this strange, we attain the same state of deformation, near to 2. So, with this information, we can make a lot of experiments for the same case, and we have different elongation for the drops. For an elongated drop, and then attain the steady state stationary. And we have the Akrivos law diagram, and we will have these marks. These marks are the drop at rest. It is, I have the drop as the movie, and then I deform and attain the steady state of the formation. That is here and here. Then you observe the huge drops, and then we attain again to the steady state of the formation. We observe that the curves are very different. Why? Because remember, these curves were made considering that lambda is 0. At rest, L-axis over initial radius of the drop will be 1. So if lambda is different of 0, this number will be different of 0 too. For this reason, we start in this position. So we made again with another ratio of viscosity. In this case is 1/10, and we observe that the curve is far different than the first. In this case, this is the drop at rest, this is the elongated drop, and then we attain the steady state of the formation. In this case, we have an interesting thing, because if I depart from a sphere in these capillary values, I attain the steady state of the formation. However, if I start with a elongated drop, the drop starts to elongate it more. So we are near to the critical capillary number. Finally, I made another experiment with ratio of viscosity of 0.25, and we have a similar case. It is curve is very different, and in this part we cannot attain a steady state of the formation. For the case of a spherical number, we start with a drop spherical, and then we cannot attain a steady state of the formation. In this part, some similar, I have the three curves for different values of lambda mu values. So finally, try to comparing with the experiments, I have to put the data at this manner with the steady state of the formation and the capillary number, and we observe this asymptotical solution that implies that we are near the critical capillary number. There are no experiments of this case. However, there are experiments for an extensional 2D flow. In this case, we have the Bentley-Stone experiments and Bentley experiments too, and we have a very accuracy with those experiments. What is the problem of this case with the other? The other is axisymmetric. This not. We have this deformation in one plane and this another in the perpendicular plane. So there is three axes of deformation. So the analysis is very different. These are the the experimental data of a stone, and this is what we do. Finally, to end, Tim always was very eager to see new things. When I start to obtain the numerical code, I start to move with linear flows in one dimension, and he says, no, why don't you use Arnold Beltrami Childress flow? And I did, and particularly this three-dimensional flow liked a lot to him. So this method is very capable to study different kind of flow, and in the future we can study the swimming of these animals that move with this function, and the method can manage swimming of the jellyfish.
Questions? Yes, John?
Is yes and no. It's very poor when the value of the lambda is bigger than 0.01. Yes, but if I study a drop with near to the zero case, I can obtain values near this graphic. However, the numerical cost implies to increase the mesh and to increase the time of simulation, because it's very difficult, because you start to see a conical length, and numerically it's very difficult to manage this this part of the drop, because it's an impinge. But the diagram works for values of lambda very, very low. Yes, however, if in the real cases, always the drops have viscosity. And this is the motivation to observe what's happening with this diagram. And we observe that happened. There is another solution.
More questions?
And in this case, the rate of viscosity is not very big, minor than 1. When the experiments are in values of 24, for example.
Any more questions? Thank our speaker again. next speaker is David Martinez del Rio from IMAS. He's going to talk about a self-consistent transport in a map model.
Hello, thanks for coming. I want to thank to the organizer for giving me the chance to give this talk. Originally, the person who was appointed to give this one was Professor Rosenbaum, who unfortunately he was unable to come today. But it's fortunately for me because of him and Professor Minzoni is that I'm actually doing my PhD in applied math. So it's nice. I'm happy to be here. So my talk is the self-consistent chaotic transport in a math model. Due to the short time that I have, I will just basically describe what does that title means and maybe talk a little bit about what we have done with the model. So first of all, I have to make some adjustment because a math model is too general. I'm working with the Hamiltonian math model, and more precisely with the Hamiltonian mean field math model. So I will try to explain what are all those things there. Then this is work that I'm doing for my dissertation with Professor Diego El Castillo Negrete from Oak Ridge National Lab and Arturo Olvera and Renato Calleja from the Department of Mathematics and Mechanics. Well, the outline for this talk I hope to feel is talk about the original model, the single wave map, the continuous versions, the discrete versions, and what we know about that map, that model, and then the dynamical systems tools that we have used to work and have some insight on what is the behavior of this map. I put these figures because the single wave map model can be applied to plasma physics and to fluid dynamics, depending on what do we do with some constant, or if we change some nonlinear terms that usually are not considered in the equations. So the original model started in the 70s with O'Neill, who was working with his group about the description of the cold beam interaction with the plasma. And they developed something called the single wave model. They put verbatim that basically the interaction that the beam had with the plasma could be described just with a nearly pure sinusoidal wave, because that wave was several orders of magnitude of what other terms that could be perceived in the interaction. So for this model, we have exact solutions that are called BGK modes. They look a bit like this, and they have some relation with this, but I will not explain what's the relation with everything. And well, in the 90s, my advisor, Professor Del Castillo, he developed it in this paper. He could reproduce these equations that were original in the original publications. He had to use a matched asymptotic expansion to get these equations, but it was the first deduction from the original equations. I will put just the toy version of how do we get those equations. We start with the Boisseau-Poisson equation. The first equation is the Boisseau, but if we change the Fokker-Planck term that we have in the right-hand side on the first equations for something like viscous term, we will have the fluid Euler equation for a two-dimensional fluid. And in both cases, the beta from the collisions or the nu from the viscosity are considered very small, so we can use this system to describe every kind of phenomena that we have in fluids in 2 dimensions without viscosity. Later on, well, this is the version that is simplified from that. I'm changing here the notation. Here the zeta is the planar vorticity, and this is the Euler equation I was talking about. I have changed what is the meaning of the variables, but it's basically the same type of equation. And we have, for the symmetry that we have in the problem, we can introduce this spring function, which is at the Hamiltonian part that I was talking in the title. And when we put this string function in the first equation, we get this evolution for this variable a that we have here in the screen function. That's the harmonic that I was telling, the single wave. And well, if just in case somebody doesn't check it, the first part is the transport, the second part is the Hamiltonian, and the third part is the self-consistent or the mean field part of the model. The Hamiltonian part actually reduced these equations to just a Poisson bracket. That's why it has a Hamiltonian structure. Later on, if we add a discretization of the planar vorticity with the point vortex representation with intensity gamma, and we separate the components, the magnitude and the phase of the A, this perturbation that we have here, we'll get this Hamiltonian model, which has 2n plus 2 equations. We have a Hamiltonian for this, but as I said in the title, this is the map model, so we have a symplectic Euler discretization. We change a little bit the variables, and we finally get this map model. This map model has 2n plus 2 equations. The first two are very interesting. The second two looks a lot, is what we call the mean field, just the two variables that express the interaction of the single wave with a bunch of point vortexes. And this is an auxiliary variable that helps us to understand the average that we are doing on the mean field. And well, the first two n equations, I said that they are interesting because they look a lot like something that in dynamical systems is called the standard map. I won't talk a lot of things about the standard map, but I will just say that we know a lot of things of it, like a lot of things. So the evolution for both models, the continuous one and the discrete one, the map, have basically the same kind of behavior. We have the cat's-eye structure. This is from the paper from Professor Del Castillo. And there's an animation of what I have done. Here we have as initial condition what I call a Fresnel initial condition. Basically, we have two Heaviside functions in the y-axis. So we have like a step, and what we have the points in black. The points in black means that there's no point vortices there. The colored ones means just that we have a point vortices there, but the colors only represent the original position of this. So the important things that you should realize from seeing the picture is that we have the cat's eye. The cat's eye may change a little bit its size, but the change of the size is what we are interested. And this is represented by this figure in red, which represents the variable kappa. The kappa is basically the size of the cat's eye, the amplitude, and theta is the phase that we have. That it's physically not interesting for us. We wish to understand what does what does this figure implies from the dynamical systems point of view. So, well, what do we know about that map? We know that if we can get the cat's eye structure, this one, and if we reduce to a simpler case, so where we instead of having n equations, n point vortices, we only have one, we can find this kind of behavior. Here, what you are seeing is a bunch of point vortices clustered together in the orbit of the elliptic of the stable elliptic point that we have for the case of n1 equal to 1 case of the map. If we have two, we can get something that my advisor likes to call a dipole. I put an asterisk next to the two because the colors not only represent the density that we have of points in this part, it also represents that they have different sign on the intensity of the vortices. Also, I failed to mention that black line that we have here and in the other case represent the size of the stable and unstable manifolds that we have for the standard map. It's just something to help us understand what's happening with the mean field variables. We also, another solution, if we have 1 and 2, it's easy to jump to infinity, which is the VGK mode, but sadly, to get this, we need an Adam-Bashford iterator, and we are not interested to try to do that with a symplectic Euler one, but we have a different kind of state with n tend to infinity state. Here, what we have is a lot of initial conditions that are just in inside an equipotential line of the equipotential surface of the energy of the Hamiltonian that we have, and this seems to be also an unstable kind of behavior for the map. So we know basically what does the map does, and just to remind it, the standard map is like this, and this is how it looks for the in the phase space, the XY components for epsilon equals 0. If we start varying it, it's the toy model for the KM theory. And the interesting thing for this is that for this map, we know that if we reach this value, we will have a global transport. There will be no KM line, KM circles. So any given condition that we get outside the resonance, given enough iterations, it can have an unbounded evolution. That's what we will call an global transport. Later on, we want to use the weapons, the tools that we have from dynamical systems to describe what does happen here, because this part it's more or less understood in the fluid dynamics, but what does these oscillations do to the dynamical system is what we would like to understand in this sense of the dynamical systems. There are some publications that relate with cases like this, but there's not one that can give us quantitative results that if we have this kind of oscillation in the perturbation parameter for a standard map, what will happen with the particles? Will it have an unbound evolution? Will we have a bounded evolution? There's not results. So we have to construct ourselves. So we decided to work with a non-autonomous standard map. We have this, it's like the standard map, but we are varying this kappa. And this problem was also a bit hard, so we choose to work with the periodic standard map. Non-autonomous periodic standard map. We start with period 2. It's the easiest one that we can get. But this one is also too complicated because, as it says here, it's non-autonomous, and there's not much results for non-autonomous maps. So we decided to work with 2 iterations of the maps of this map. If we work in pairs of iterations, what we get is this map that looks complicated, but it's a map. But it also can be written as a composition of standard maps. And that's not a twist map, so some results that we have in dynamical system does not apply here. Nevertheless, we can get some results. The blunt weapon, the most blunt weapon that we have in the dynamical systems arsenal is to use what we call direct method. Professor Simó in Barcelona called the brute force method. And it's also, the actual name is Chirikov crossing method. But basically, we choose a lot of initial conditions in a given set. We let them evolve with the map for a given set of parameters. If there's KM theory, if there's KM tori, the evolution will be bounded. If we trace in some way the parameters, maybe that torus will be destroyed, that circle, but there may be another invariant circle that will persist. But if we insist, eventually we will have an unbounded evolution, so we will have global transport in this map. And well, this is what literature called the Chirikov crossing method. And using this kind of reason, this process, we could find this figure in the parameter space. If we choose parameters inside the horns, we get bounded evolutions. If we get parameters outside the horns, we get unbounded evolutions. So in Spanish, it's very funny to have to look for tori and find horns. But if you don't get it, don't worry, it's a bad joke. So if we have tried the most blunt weapon that we have in the arsenal, But we also have the most sharpest one, the most recent one, which is called the parameterization method. I don't have enough time to explain how it works, but there's a lot of reference, and the name that people should recognize, should know, is Rafael de la Llave. He's like the authority in every a posteriori KM theory. And we were lucky enough to have in the department an expert, a student from Rafael, Professor Renato Calleja, who helped to implement this algorithm for our computations. Using the parameterization method that I won't explain here, we could complete this figure. This is just the global transport that we have here. If we want to know what happens with the golden mean toroid, that golden mean invariant circle that we know is the last one in the standard map, we know that near here, near the axis, we are working exactly with the standard map, basically with the standard map, and these are supposed to be the best boundary that we could get analytical. But here we are supposed checking the symmetries of this map. We know that the best one is twice the golden mean. And for the other side, by symmetries, we can complete this figure. And we were very happy because, well, nobody has studied this map. We could find boundaries, use the results, powerful results from the dynamical systems to give some sense to what does this map say. And when we sent this paper to be published, the referee asked us, can you estimate the critical points, the critical exponents? And we were wondering what exponents, because there are several ones. If we want the general geometric ones, we need more tools, because nobody has estimated periodic orbits for this kind of map, because this map is what in literature called a non-reversible map. So we have to go back and invent a new tool to work with that. And we also had another questions, work in progress. We know what happens with two parameters. If we had three, we were checking and we found a very odd structure here in the K1 equal to kappa 1 equal to kappa 2 versus kappa 3. We get a fractal structure here, so it really gets annoying to find fractals everywhere. And we could get something more complex. We have done the 2. For 3, we had that figure. If we get P, we could get something more nasty. And while trying to give some answers to the referee's answer, we started to modify the parameterization method to find periodic orbits. These are Fibonacci ratios that are a good approximation for the golden mean. We could find periodic orbits. This is just one of the points for different periods. We could use the parameterization method, the modified versions, to get something with a raw approximation of where are the periodic orbits, and then we use a 2D pseudo-Newton method with a lot of things inside to get it to a more reasonable error. And we are working with that. The residue that I'm putting here, well, it's relevant if you know what does that mean. If not, it's something that I'm putting in the work in progress because it's work in progress for my dissertation. Well, there's some reference that you may want to check if you're interested in the topic. Thanks for your attention.
Are there any questions?
Well, he could have asked what will happen with 3 parameters or with n parameters if we have a general idea, because I didn't put it here, but if we, instead of checking what happens with 2, we try to work with a more general map that appeared in some of the reference. These general horns that we found are a good bound for the existence of a toroid in 3 dimensions, which is like talking about not period 2 or period 3, but period infinity. So it will be more general, very important to know what does this blue line mean. but the referee was had reasons to ask us about the geometrical exponents or constant that we help to describe what does these lines mean in this border, because it will answer or help to generalize some results or to understand if some results are still valid here that we are working in non-twist map in different cases.
Any other questions? Okay, let's thank our speaker again. Our next speaker is Juan Carlos López Vieira del Instituto de Ciencias Nucleares en la UNAM. The title is 357 Bodies Choreographies on the Lemniscate.
Okay, good afternoon. First, I want to thank the organizers for giving me the opportunity to talk in this conference, in this workshop, honoring or to the memory of Tim Minzoni. I remember him in all the seminars we attended. He was always full of questions and proposing problems, and we for sure will miss him in our seminars. And probably this problem will be one of those which he will like very much. So I'm going to talk about choreographies of 357 or N bodies on the Lemniscate. Let me begin. So here I present the abstract. In 2003, Fujiwara, a Japanese from Kyoto, discovered a remarkable three-body choreography on the Lemniscate for which the potential is found explicitly and depends only on relative distances. And here we present some arguments to demonstrate that not only 3, but 5, 7, etc. bodies can move in choreography in the Lemniscate. So first, a definition, a choreographic motion of n identical bodies is a periodic motion on a closed orbit, chasing each other on the orbit with equal time spacing. So this is the definition of a choreography. And then a small history. Everybody knows that the Newtonian gravity problem is easily solved for 1 or 2 problems, but for 3 problems, for 3 bodies, it's already non-trivial. And in 1993, Chris Moore discovered an amazing closed periodic trajectory for 3 bodies of equal masses, which is called figure 8. And later on in 2000, there was a rigorous proof of the existence of this trajectory by Chanciner and Montgomery. And later on, many more remarkable choreographic of n-body bodies were found by Simon and other people. So All this was for the Newtonian gravity problem, and motivated by this amazing trajectory, Fujiwara, Fukuda, and Ozaki tried to understand what kind of figure is this. So we know that the Leibniz gate is a figure-8 curve, and so they were trying to study the choreography of three bodies on this Leibniz gate, and so they found this choreography explicitly and on this Leibniz gate, which is an algebraic curve. So this is the fourth order or 4-degree equation for this curve. This C is a parameter of scale. This is for C equals to 1. And this curve can be parameterized by the Jacobi elliptic functions in this way. So this is X, this is Y, where T plays the role of a parameter, K is the elliptic modulus, and the period of this curve is 4K, where K is the complete elliptic integral. So this is the notation. So what Fujiwara did was to place three particles here, equally spaced in time. So here we have the coordinates for the first, second, and third body, all of them with equal masses. And on the left, you see actually the animation for this choreography. The first thing we have to solve is to ensure that the center of mass, which is depicted here in red, is staying at the origin. And this requires a very specific value for the elliptic modulus, which is given here for this problem. And actually, this value of K fixes the initial data, which leads to this trajectory. We know that in general, for arbitrary initial conditions, we can have an arbitrary curve, but for this value of K, the curve is exactly the Leibniz gate for this problem. So one of the things we can do to see how this value of the elliptic modulus has to be this value is by the following animation. Here we plot the x coordinate of the center of mass as a function of the elliptic modulus, and you see as the time varies, there is only one fixed point here which corresponds to this specific value. Otherwise, the center of mass motion has a motion which is probably harmonic or something like that. So more important, perhaps, is the fact that this choreography satisfies an equation of motion on the two-dimensional attractive force proportional to the inverse of the distance with an extra repulsive force proportional to the distance. So they found an explicit potential because the force is conservative. So they found this potential for which this force can be written in terms of the potential. And for this, they found two relevant constants of motion, which is the product of the three relative distances squared. And also this other constant of motion, which is the sum of squares, which we may call the hyperradius in the space of relative distances. Both of them are constant, and they are S3 invariant, so we can interchange the or permute the three particles, and they remain the same. So based on these constants, Fujiwara found this form for the potential, which is this part corresponds exactly to this attractive force proportional to the inverse of the distance, plus this, which is a harmonic oscillator type force, only with a reverse sign. So it's an inverted harmonic oscillator part. So this potential can be written in terms of those two constants of motion of this type. And so, well, they found this potential, and for this potential, the equations of motion, the Newton equations of motions are satisfied. So it's a true choreography. There are many conserved quantities, among which we can mention that the angular momentum for this trajectory is 0, total energy is conserved. Those two are global quantities, global conserved quantities, but there are others which are only constants along the trajectory. These are the moment of inertia, the hyperradius squared, the sum of squares of the curvature, the kinetic energy, and maybe more, which are dependent. So the Leibniz gate for the three-body is a particularly maximally superintegrable trajectory. What it means that along the trajectory, we have several constants of motion, which Poisson commute, or the Poisson bracket with the Hamiltonian on the trajectory is 0. This is the definition of a particularly integral of motion. So in this case, after removing the center of mass degrees of freedom, we have 4 degrees of freedom, and for a superintegrable system, we need 2n minus 1 constants of motion, which are 7. 2 of them are global, 5 particular. So it seems that this feature is more general. And so Sasha Turbiner's Turbiner conjecture that for any closed periodic trajectory, this trajectory has to be particularly maximally superintegrable. And for this trajectory, for three bodies, this is the case. So, so this is an interesting question. If for any other closed periodic trajectory, this conjecture is valid. So now, let me move to the 5 bodies on the Leibniz gate. Here we have also 5 bodies. The parameterization, or the indexing of the coordinates, goes like this. The first particle has an argument t minus 2 times the period over 5, etc. And if we plot the x coordinate of the center of mass as a function of the elliptic modulus and vary this on the time, you can see that there are 2 fixed points, one here and another there. So apparently, there are 2 values of the elliptic modulus for which the center of mass remains at the origin. And we can solve this numerically with Maple, and actually these are the 2 values, which we will call k1 squared. These are the squares, and k2 squared. So if we make an animation of those 2 possibilities, they look like this. So this is for the first value of k1, k, which is called k1, and we have 5 bodies which chase one after another, and they are labeled 1, 2, 3, etc. And this is for the first case. This is for the second case. Here, you see that around here, 2 particles seem to, or they approach very quite close to each other, while in this configuration, the distance more or less remains the same. Okay, so these are apparently choreographies, but in order for them to be true choreographies, they should satisfy some equations of motion. And this question is very important. Actually, we were not aware, but the same authors, Fujiwara, Fukuda, and Ozaki, published another paper in some Japanese journal. Actually, I don't know exactly the reference, but it's called N-Body Choreography on the Leibniz gate. And they said that they also investigated with the same parameterization, but different number of bodies, and they found that it may not satisfy the equation of motion under any interaction potential, which means, unfortunately, it is not an n-body choreography. So, and they even more, they write, or at least it's very difficult to find such equation of motion. But nevertheless, we tried. So we started to explore the conserved quantities for the two solutions of K, and again, the angular momentum and the total energy, well, assuming there is a potential, those are global quantities, but also the moment of inertia, the hyperradius, and the kinetic energy, they all of them have well-defined values, so they are constants. But then the question is, what is the form of this potential? So the first attempt was to choose a similar form to the one proposed by Fujiwara, only perhaps with different coefficients, alpha and beta here. And in this case, this potential, because we consider all 10, in this case we have 10 relative distances. No, I'm sorry, 5. So, well, so this potential is invariant under permutations. Maybe I'm wrong here. So, so we tried this potential and calculated the equations of motion, and they were not satisfied for any alpha or beta. So we didn't find a solution for alpha and beta such that this potential satisfies the Newton equations, which are written here. So what else we can do? Well, we remember that there were some relevant conserved quantities for the three-body case, which is this product, and which is invariant under permutation. But we started to test several combinations of products, say, again, 3 out of the 3 out of all the possibilities. And we found, by exploring each one of the possibilities, that this quantity is also a constant of motion for the first value of K, and this is for the second value of K. You can see that the relative distances involved here, which are 5, they are so they belong to different separate sets of relative distances here or here. So they are 2 complementary configurations leading to those 2 choreographies. Moreover, also the sum of the squares of the distances in each configuration, they are also constant. So, and the list of possible constants of motion here is not exhausted yet. We can explore more. So, because they were constant, these quantities, so if you take the logarithm, sorry, if you take the logarithm of this constant, you can build another potential which looks like this, so for the first and second values of K. So in this case, it's not invariant, it's not permutationally invariant. This part, however, it is. And so we explored actually for those products all the 252 possible configurations, which are 10 choose 5 among the possible relative distances, and this is for each case, so, but it's not a big deal. So the potential can be written in terms of those, in terms of this constant of motion, and in terms of the hyperradius, which is given here, which is the sum of squares of all 10 relative distances. So the potential can be written like this. So the question is, can we find coefficients alpha 1 and beta 1 or alpha 2 and beta 2 such that this potential satisfies the Newton equations? And the answer is yes. So we found for both cases a solution for alpha and beta which satisfies the Newton equation. So first solution for the first value of k is alpha 1 is equals to 1/2 and beta 1 is this number. And for the second case, alpha 2 is 1/2 and beta 2 is this number. So, well, so it means that we have true choreographies because they move in choreographic motion, but we found a potential for which there are some corresponding Newton equations. And so again, we can ask the question, if the Leibniz gate now for 5 bodies is a particularly maximally superintegrable trajectory, so Turbiner's conjecture. In this case, for 5-body case, the maximal superintegrability, counting number of degrees of freedom, etc., is characterized by 15 constants of motion. We know some constants, but we still need to find the others to to prove that also in this case this conjecture is satisfied. We still don't know. So what are the missing particular integrals in this case? Well, this is ongoing work. So how much time do I still have? 20? 2 minutes. Well, only very briefly. So for 7 bodies on the Leibniz gate, here we have a choreography. In this case, doing the same research, we can find 3 values for k such that the center of mass is at the origin, and repeating the same, exploring. I will move faster. And this for the first value of k, we found that this is a constant of motion. And for this, we explored all possibilities for 7 out of 21 relative distances, which is this enormous number, 116,280 configurations. So we evaluated those quantities at different times and see the difference, and if the difference is less than some threshold. So we test that more carefully, and we found that this, for the first value of k, this is a constant, or the previous one, this one. So actually I didn't mention, but with the labeling I placed, this looks very natural because this is the distance 1, 2, then 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, and 7, 1. So it's quite natural, so we can make some generalization. So in this case also, we can find these constants here. This was alpha 1 for the first case, but beta for the first value of k, which is the only one we have explored so far. We found these values for which the Newton equations are satisfied. So even for 7 bodies, this is a true choreography. Again, we may ask the question, is this a particularly maximally superintegrable trajectory? In this case, we need 23 constant of motion. We know very few, but so, well, we are confident that we can find them. So, conclusion is that choreographies of 5, 7, and possible any odd number of bodies on the Leibniz gate exist. For 5 bodies, there exist two possible choreographies corresponding to 2 possible configurations of 5 of 10 relative distances, which correspond to 2 solutions for k, such that the center of mass remains fixed at the origin. And for 7 bodies, there exist 3 possible choreographies corresponding to 3 possible configurations of 7 out of 21 relative distances, so 3 solutions for k such that the center of mass remains fixed at the origin, and the corresponding potentials were found such that the Newton equations are satisfied. So they are true choreographies, which is a result which the Japanese predicted to be very difficult to prove or to find. So thank you, and again for giving me the opportunity to talk to the memory of Timon.
Are there any quick questions? There's one more speaker, and the bands are leaving at 4:45, so please be brief. Yes.
Excuse me. They collide. So we cannot find, for even number of particles now, they collide.
Alejandro?
Well, I don't know. It's very close to the sun, but these choreographies are for equal mass bodies, so maybe it's a very different problem.
Yes, Sasha? Any other questions? Let's thank our speaker again.
Está bien, a las 20. Sí. Nunca. Sí, está cerrado.
este.
Our last speaker is Alejandro Aceves from Southern Methodist University. The title of the talk is
¿Cuál es el
Recent
point?
Trends in Nonlinear Optics and Photonics, a Mathematical Modeling Perspective.
Thank you. Thanks to Panos, Gustavo, Arturo. It's always been very special for me to come back, and these guys have done a tremendous job for this conference. Perhaps the most important member in the audience is Clara. I told her to get up in 20, so we go home. If she falls asleep, I'll keep going. Okay, it's a warning. But you will see once I get into the technical part why I could stop at any point, and it's not a big deal. So, of course, dedicated to TIM, a common myth. I was not a student of TIM. I took courses with TIM, but I did my undergrad thesis with Jorge Ise. Yet when there was this dichotomy about Courant or the Courant school or the Caltech school, because my undergrad was in physics, I was more interested in getting closer to physics, and so the rest is history. So of course, there is no question that it was a strong impact. TIM has a strong impact on my career, but it's in a little bit of a different way. I'm a little bit of an outlier with the rest of the audience because I was not his student. I've only done I co-authored one paper, but really Luis was the central part of this. I mean, it wasn't a long communication between Tim, Luis, and myself. It was Luis and telling us what he was doing. Yet, as I said, for me, 30 years has been the following. I come, visit family, come to a conference, do both. I always stop at Imes to say hi to my friends, and I go to Tim. And we have a conversation in his office. There's this curious problem. It looks like I think we may be able to do this with a very vague premise, only looking at being interesting and then absorbing knowledge. So a little bit in what Michael said, the good problems are still coming, and I want to do it forward-looking. And if anything, I would say, what would Tim say, or how would Tim go about this? So the style of my presentation, knowing that was the last one in the afternoon, was purposely, imagine I have a communication. I'm here visiting Tim, and I will talk about problems that are poorly understood. So there is no nice results. Trying to bring in some ideas, why they are interesting, how they are connected. And now you're the audience. You're like, Tim, you have to help me figure out how to solve the problems. So last night we had dinner, and there was a puzzle. Who was Tim's first undergrad student? When he came back, there was really no grad program in applied math, so there were undergrad students. And I threw it to the friends. We went for dinner, and only one person figured it out, Gustavo. So I think this is true. If it is not the first, it might have been the second or the third, but, and I'm sorry for the color. The title of the bachelor's dissertation is Algunos problemas de propagación de ondas en presencia de playas. So it's propagation of waves approaching a beach. The student is Adriana del Rocío Hurtado Romero. Some of you know them as Adriana. Others know her as Rocío. I know her as the boss. So that's how the story goes. So, and I think she was the first one. You see, you were not thinking outside the box. Okay, so we'll see how far I go until Clara gets out and gets up. I will showcase a few interesting problems that are emerging in nonlinear optics. I call it nonlinear optics with a twist, and you will see why. And we'll see how far we go. Doesn't matter. The first thing I want to say is, in the current field of optics and photonics, the new element that is coming is add helicity, add topology. Imagine the fibers that people have drawn for propagation. So this would be the direction of propagation, and you twist them, then you couple them. So in some ways it's photonic-like, periodic-like, but with an added degree of freedom called helicity. And when you look at dispersion relations, you get this interesting thing called conical. So this is a dispersion relation. You get this singularity at the origin in and this is working at Penn State. It is this type of singular points are sometimes are called the Weil cone, the Dirac cone. So the point of it is, in optics and photonics, we've been in some ways blessed by having concepts that come from quantum mechanics and now even mathematics. Last year's Nobel Prize had a lot to do with this, that you can always test and look at behavior in a photonic structure. So the singularity in dispersion relation, instead of having a smooth and maybe a gap, you cross and you have this singularity in the dispersion relation. And this is the addition of topology, and it has consequences. So what type of twist I am thinking about? Well, if you put twist in multimode fibers, that means many modes. So suppose you have a many mode system like the Schrödinger equation. You put a twist, you put some sort of angular momentum that assists into coupling many modes, and it couples in beautiful profiles. So this is, you can see why people are really looking at this. This is just theoretical. It's an ongoing research of interest. Another element is to put these multi-fiber arrays and twist them. And actually, they are the people have built up these twisted multi-core fibers and done experiments on it. Those of you who like to see equations, you go the classical in the nearest neighbor interactions for multi-waveguides is nearest neighbors coupling, and the twist creates a complex phase in the coupling. If you go beyond any type of topic that has emerged also in optics, is this parity time. You can put a gain and loss, but if gamma is equal to 0, then you have a conservative system, and the twist changes the way light propagates in many modes. And this is a more complete work. I wanted just to give credit to my former student, postdoc, Claudia and Yanan. So I will not talk about it because it's more complete. Instead, I will talk about something that is interesting, and I have some ideas. This is where I would come to them. Look, here is this problem, and this is what I think it is. And in some funny ways, in fact, Gaetano, in a similar system, thought the same way. Interesting. So what happens if you have what is called a photonic crystal fiber? So the dark are air holes, and the other one is silica. There is no central core of silica, so there is really no guiding. If you solve the mode, it is called a Bloch wave. If you look at intensity, obviously the light likes to concentrate in the beautiful profiles in the core areas, but it is extended. This is not a confined mode. And so this is an experimental work by a group in Max Planck in Germany. Philip Russell is the lead. And this young guy was giving a talk a year ago at an applied math institute. So here are the experimentalists coming to applied math and showing some work and with little understanding of the modeling. So what happens is when you twist, and the twist rate is here, it's radians per millimeter, what is happening, and here's the experiment, is what used to be an expanded mode, it confines. So light tries to stay trapped in a confined mode, and there is this, because of the rotation, there is, if you look at intensities, how it decreases as you extend, it's kind of radial, the degree of localization. And the faster the twisting, the more confined it is. So here is a simulation, and here is what they write in this paper. In, what is it? I think 2016, November 2016. So the curved periodic space creates a topological channel, which light can be trapped with a confining strength that scales with twist rate. And then they talk about an effective potential that is generated that is quadratic in the radius. You look at the paper, and they just begin to suggest ways to explain it. And they did it using ray theory, Hamiltonian ray theory, and they write an equation without any justification that says that the paths of the rays are confined in an ellipse, but no real justification. So can we model this? Can we say how it is that it is confined? So if we were to use ray theory, a ray approach, we know that the paths of the rays minimize this Lagrange, the index of refraction. Now the The Lagrangian in this case is, I mean, this is just a model. It doesn't matter the profile, except that it is periodic. But then there is a twist. So you change variables to the twist. And again, you know, I'm going fast because really this is rude. This is just an exercise, a thinking process. What if I do this? And we are only seeing certain features that suggest maybe we're going the right way. You do this rotation transformation. Z, remember, is the equivalent of time. And here is length in propagation. And you identify a small parameters. This is the rotation rate, time, the characteristic distance between the lobes in the photonic structure. Something that I don't understand from the paper, they say, we're going to do ray theory on the block waves, not on the plane waves. So there is already something I don't understand, but I didn't stop and I just say, well, let me do a little bit of understanding what is a small parameter, what does the transformation does if I put it in the Lagrangian. So there are two ways in which I could go. One is, through this rescaling, first the rotation and the rescaling by this characteristic length, and the rescaling of the effective time by the rotation rate, I can go into a new set of variables in which the small parameter appears. If I do a little bit, if I do just an expansion of the length, the arc length, and then I get something that looks like this. And what is interesting, once again, the mechanical interpretation, you have potential and kinetic. Notice that in the potential I created a parabola. So maybe there is something to be said about this analysis, because here is the original delta n in a rotating frame, so it looks frozen, and then there is this parabola. What is interesting, and it has, I think, to do with a little bit of the twist, some sort of momentum that is not quite understood. This is the usual kinetic, but there is this other term. So is this the right way? What is the interpretation of this? I don't know. So before I went on, or we went on, this is, right now we're doing it with a PhD student of mine as a little bit of a toy problem. Instead, you could stay in the, without doing the rotation, and just try to, there is a small parameter, so you simplify the effective Lagrangian density. And if you write equations of motion, then you get, so you go all the way to the dynamics here, and the idea is whether these dynamics suggest confined orbits. So I don't know. You know, I would say, Tim, am I going the right way, or should I just stop and go somewhere else? So if he were to say, this is nonsense, go somewhere else, well, where is somewhere else? First, by the way, when this guy talked about it, I said, what you have created is the Kapitsa photonic crystal fiber. Because the analogy is this unstable point, and if I put a little bit of momentum, k, then you access all possible ranges because it's unstable. That's the broad representation of the field, the block wave. If you shake it, and the more you shake it, the less these deviations of the let me go back. The less the deviation of these things, which would mean the confinement. It is not clear that it is called a Kapitsa because in the scales, the helical twist is apparently still too slow. But in any event, I mean, this could this be a Kapitsa effect? And a group with Gaetano did look and did talk about the same concept in a similar system. But as I said, I'd rather go and maybe use field theory, instead of ray optics, go to field theory. So what is field theory? It's just the linear propagation equation. So already is for the envelope. So this is the usual Schrödinger equation, and you have an index of refraction that depends on z. And the z dependence is on the twist. So what happens if I do the Schrödinger equation and I apply this rotation transformation? The Laplacian stays invariant in the UV, and you get this kind of angular momentum, this twist effect. There should be an I apologize, there is an I here. And the thing is, again, by putting at the scaling arguments, there is a 1 over epsilon term in front of the Laplacian, the effective eigenvalue, and in this case, the frozen index. So if this is correct, if we didn't mess up on the scaling, what it's saying at first order, you have the block wave. So the structure of the mode doesn't change. Okay, it has this hexagonal feature, if you notice. So the 1 over epsilon captures the block wave that I call B here. And so that balances this term. Then this is anticipating, and try to see if I'm right, that there is a slow function. So we put an epsilon here that is radially symmetric, and that's the confinement, a prefactor. And then, by the way, what is missing here, it's evolving. There is also z dependence. And then there is a phase. There has to be a phase. You put twist, you modify the phase. It's called a gauge transformation. So the idea is, can I go to the next order? The 1 over epsilon is solved. What happens at order 1? So there would be a few terms from here in terms of the derivatives in f. There would be a few first order terms here that only come from the b. There is also parts that depend on the phase. The phase has the same functional form, we assume. So you get, from the real and imaginary part, two types of equations for phi and for f, all factored out by derivatives and functions that depend on this fast spatial scale. So this is homogenization. So the project would be, can do the spatial average and the homogenization. So try to average on the fast scale, which is the scale of the block waves, to try to characterize f and phi. So in principle, that can be done. Do I get equations that for f really go and decay to 0? We don't know. So those are the ideas we're floating here. So last year I was visiting an institute in Bilbao, in Spain, and a group of Enrique Zuazua, and they all talk about control theory, and I was trying to learn something new, and they all talk about the fractional Laplacian. It's a key operator that is relevant there. And I said, well, is there a fractional Laplacian in optics? If I can translate what they do, which is in a diffusive process, to optics, maybe there is something interesting that we can look at. And coincidentally, we found a paper by Longhi, in which, in a cavity, Gaetano had a little picture of a cavity. This is another way to do a laser. His was with no cavity, but you bounce light back and forth, and you have functionality. Basically, because we don't have the time, she's about to stand up. With a lens, you manipulate and you scramble the K wave vectors. With masks, you create, you affect the phases in such a way that it acts like a potential. And so you do what is called a master equation. After many trips, you create an artificial time evolution. It's the round trip time. You get a time derivative from a map. And lo and behold, you can get a fractional Schrödinger equation. So fractional is because the derivative, in the Laplacian, you have, instead of the second derivative, there is no, it's not one. This is and there is the parameter which tells you the degree of fractionality. Now, there is always the magic. I love when you connect things, and I mean, I would imagine how Tim would jump up and say, well, of all these cases, look at this equation, and let's assume the steady state. If alpha is 2, then, I'm sorry, if alpha is 1, so if I say, let's study this equation in K-space, the Fourier transform. So if I Fourier transform, if the fractionality gives you K, although it's a little bit tricky, it's mod K, not K, it would be mod K. And if V is your favorite potential, the quadratic potential. So x squared phi in the Laplace is the second derivative in K. This is K times the Fourier transform of phi. You get the area equations. So they come all over the place. So in Fourier space, the fractional Schrödinger equation with a quadratic potential for a particular alpha is the area equation. And it is not surprising that the type of modes you can create from these cavities, I mean, this is still numerical, have memories of these profiles. Non-localization, this is the classical thing. You send Gaussians in a cavity with traditional lenses, and wherever you get something confined. But you mess up with the fractionality, you get other structures. And so people have looked at this in propagation. There is a recent paper, October 2017, what happens when you send airy beams, and what does the degree of fractionality does to it. So in terms of, does it confine, does it expand, locality versus non-locality. And we also like in our optics to look at discrete systems. So is there a discrete system that is connected to the fractional nonlinear, the fractional Schrödinger equation? And if I put nonlinearity, our favorite one, it is this long-range interactions with a particular algebraic decay. So there is the 1 plus Ts. So there is a discrete system. It is non-local, long-range interactions. They have not yet talked about it in an optical setting. They talk more about proteins and DNA because of the folding and configurations. You have a chance to talk to not nearest neighbors, but to everyone. So, so here it is. And I believe in optics now the equivalent, oh, that's it. If you put nanoresonators, you can engineer, I believe, an optical system in which the oscillators are nanoresonators, and you can really build up. They are so tiny, and the platforms, the chips you can put it in, you may create this. So an open question, the last one, under which conditions you can apply the continuum limit. And if you can apply the continuum limit, what is the degree of fractionality in the continuum versus the long-range interaction? Very little known about this. And with that, I will stop. Thank you very much.
Are there any questions?
Yes,
John?
John. Right, right. At this stage, is the only way. So, in fact, and here is the connection with the previous work, I mean, this idea of engineering singularities in your dispersion relations. So with alpha fractional, you create also singularities if you look at the linear dispersion. They will. We don't know why, and by the way, Luis, I mean, things that I didn't show up here, Luis has been doing simulations. We did a little bit of the WKB to see effects on group velocity, transport, all these things. That, you know, and what stands out at this level right now is indeed that one of the things that is curious in connection with my first part of the work is this formation of a singularity in the dispersion relation. Exactly.
And you haven't finished that little homework exercise of the ray optics that you showed in the beginning. And is it because you think it's a less likely, less significant model than the fractional Schrödinger equation model?
Two answers, and I'm a bit lazy and I'm not very smart, so give me more time and give me more advice. No, I mean we just threw it up to I mean, as we all know, as we all do, if the very first crude thing shows you something interesting, we should follow up. But this was done 2 weeks ago, and last week I was away, so it's more time. No, but I also need your advice.
Yeah, I'd like to see more of that.
Yes, sure.
Sasha?
Of course, understanding what does it mean nonlinear Schrödinger equation exists, we understand. But fractionality of derivative, you have some physics intuition about this alpha?
Not that I don't understand, but and forget about the nonlinear, because the nonlinear can come, you know, if you put it in the optics. But let's look at more than once, because of the, if I go to the field representation, forget about the nonlinearity. So going the wrong way. This was the last one I didn't even show you. But if you just look at the Schrödinger equation, so forget about nonlinearity. In optics, there has always been a quantum mechanical proposal, like in parity times symmetry. You know, why can you make a potential complex, and it would be only relevant if the spectrum is real, because that's energy. And they added this parity times symmetry. There is Anderson localization, not proposed, but only in optics. So if you, and don't ask me the details, but if you do a Feynman path representation of quantum mechanics, the plausible trajectories of the Feynman path in your path integral representation are nearest neighbors is diffusion, diffusion-like is local. If you have, and here the analogous is, and it relates a little bit to control, if you have a strong departure, a Levy flight, which also begins to be consistent with the discretization because it makes it non-local. So if you allow in your statistics Levy flights, strong departures of the class of paths, path integrals, your quantum mechanics will give you the fractional Schrödinger. That's the only the physical one for quantum mechanics. For optics, all you have to do is design perhaps a non-trivial lens, but a lens will do it. In Fourier space, all you have to do is a functionality of the vector, of how you scramble the vectors, the wave vector.
But in this case, you should forget about interpretation through Feynman integral.
In which case? In the classical?
In the case when derivative is fraction.
Yes. Yeah, I mean, I'm not touching the quantum rule. I just say that believe it or not, there is a paper that in quantum mechanics that brings the fractional Laplacian as opposed to the classical Laplacian, and in the context of the Feynman path interpretation. Not that I will do any. No.
Yeah, John again.
Actually, I have a proposal for you.
Thank you. Sorry. Okay, square. Right. Okay. Right. Now it's interesting. The mod K is unique in its own characteristics, and it connects. As I said, that's the one that connects to the Airy profile in the Fourier space. But one of the things that you can do is also spanning to K. If your initial system is discrete, you can in principle tune in the degree of algebraic decay of the coupling. And so that would be a little bit of the tunability, but not only the validity of the continuum, but the tunability of the degree of fractionality.
Any other questions? Yeah, Panos?
The problem of the twisted fibers, in your model, it seems like you have a potential that depends periodically on zeta, on
yeah, but
on
remember
time.
This one.
Yes.
The one that I did.
No, above the first.
Yeah, above.
equation.
But then I do the transformation.
No, but
rotation.
without doing the transformation,
yes.
it just describes a periodic.
Yeah. And that's the type of thing.
Yeah.
I don't think you did the transformation, the rotation in the previous, but yes, this is
So
just
you're saying
periodic in propagation.
In this problem, you have localization or initial condition. I think that maybe in initial conditions that's localized disperses slowly, or
Yes.
is that?
I mean, if you do the numeric, of course, like any experiment, this is a finite propagation. So you may be slow in the leakage.
Mhm.
I believe because there may be leakage because there is air holes and whatever. So it may be really that you are slow in the leakage. So maybe these asymptotics may only be valid for us, z to certain order. But you are right. The physics, I think there will be eventual leakage, and the thing will not be fully confined.
And this is all non-linear.
This is linear.
And
This is
okay.
linear. And of course,
All these systems, all this above the pictures. Is not
yeah, and the point is because if you remember in optics, the effective nonlinearity only comes when you factor out the area where the light is. So here you cannot make oops. For this one, in terms of the optical application, it doesn't make sense to do the nonlinear case. It doesn't mean that there are others like the arrays and whatnot, but on this one, no. The only relevant one is really the linear case. But it's still interesting, even the linear case. There is a paper. So you want to look at this. I mean, I haven't done anything. The only paper I know, and it was presented last week also at Siam, is direction I go. Look at this paper. This is a group. I think she's at Penn State and somebody at MIT, and they. No. Oh, here. I'm sorry. This is the paper to look at. You can even see the title. It tells you the story. And this is for the nonlinear Schrödinger, not only the linear. And so this is Jake Kirkpatrick and other co-authors, one from MIT. And it is mathematical. Right. That's what this is what we are here for, to connect. Yeah, but this is a good paper. And it's interesting because there is not a one-to-one. There is either it fails or it works, the continuum limit. And when it works, it's not there is a universal alpha in some instances. So, intuitively, if the S is large, the interaction becomes more localized, and the continuum NLS is a good one. So it's not that you have to tune the alpha. It's alpha equal to 1. But if you are more long range, there may be, in some instances, a validity, but alpha depends on S, and in others, there is a breakdown of the approximation, the continuum approximation. I mean, that's the gist of this paper. The rest is in the details.
Any other questions? Let's just thank all our speakers today.
Thank you.